So, in the last class we had started our discussion on diffusion and dispersion, diffusion of mass specifically, and I had said that we will be considering estimating the diffusion coefficient for what are called gases of hard sphere molecules. Okay. So, these are molecules which interact only when their surfaces touch, as would hard spheres, and they do not interact otherwise, in contrast to regular potentials which are attractive up to a certain distance and then repulsive below that distance. And so, the diffusivities we calculate will go as square root of the absolute temperature. This is a model. Real gases do not necessarily follow this. We will be using this only to make estimates of the diffusion coefficients in gases. For more accurate quantitatively accurate results, you need to look in tables of properties in order to get quantitative values of these diffusion coefficients. So, last class we started looking at mass diffusion in gases. Diffusion takes place because of transport of molecules, physical transport of molecules across a surface in gases. Recall that in gases, in the kinetic theory of gases, the distance between molecules is much larger than the molecular diameter. So, the molecules can be considered as points, and they are under a constant state of fluctuating motion. The energy in each translational mode is half kT. Therefore, the total energy in translational modes, the 3 translation modes, is 3 by 2 kT. This is related to the fluctuating velocity of the molecules through half mv RMS square is equal to 3 by 2 kT. Mechanism of diffusion: if you have a surface in the gas and there is a variation in the concentration of one particular species across that surface. Okay. There is a concentration variation across that surface. There is a net diffusion flux because molecules coming downwards across the surface are coming from a distance of the order of one mean free path above the surface. The molecules going upward are going from a distance of the order of one mean free path below the surface. The concentration at these two locations is different. If the concentration is higher on top than it is below, there will be a net flux of molecules downwards. The flux proportional to the product of the root mean square velocity and the mean free path. Okay. With factors A, J and B, which are numerical factors, dimensionless, of order 1. We got this result by taking the flux going upwards, downwards, from a distance of the order of one mean free path above the surface, and the flux going upward from a distance of the order of one mean free path below the surface, and expanding out the concentrations in this parameter lambda, which is the mean free path. This expansion converges only if the mean free path is much smaller than the macroscopic scale, the length scale over which the concentration varies. Okay. So, if the mean free path is much smaller, the micro scale in gases is the mean free path. If it is much smaller than the macro scale, which is the length scale L for the variation of the concentration here, okay, then you can use a Taylor series expansion and truncate at the first term. Turns out the 0th order terms both cancel out because they are related to concentration at the same location, and therefore, the flux is proportional to the concentration gradient dC by dZ, okay, at that surface at Z is equal to Z naught, with a coefficient in front, okay, which is the diffusion coefficient. There is a negative sign here because mass has to transport from regions of higher concentration to regions of lower concentration. So, the diffusion coefficient is some constant times the root mean square velocity times the mean free path in a gas. We had estimated both of these. the root mean square velocity from the equipartition of energy for in kinetic theory of gases. Vrms is equal to square root of 3 kT by m, where m is the molecular mass, Kb is the Boltzmann constant, and T is the temperature. The molecular velocity turns out to be approximately 2000 meters per second in hydrogen at room temperature and pressure, because it has a lower molecular weight. Common gases such as oxygen and nitrogen, it is of the order of 500 meters per second. It is also comparable in magnitude to the speed of sound through the material. So, the diffusion coefficient is basically the molecular velocity or the speed of sound times the mean free path times a constant. Mean free path we had estimated by examining how a molecule travels between successive collision. It traces out a path along which there is a cylinder of exclusion, such that if the center of a second molecule is on the surface of the cylinder, that means the distance between the molecules is 1 molecular diameter, the surfaces have touched, a collision has taken place. Based on the fact that the length of the cylinder is going to be the mean free path when the number of second molecules is approximately 1, we had estimated what was the mean free path. It goes as 1 over square root of 2 pi into number density times dm square, molecular diameter square. So, it is inversely proportional to the number density, inversely proportional to the square of the molecular diameter. And we had again estimated this in some for hydrogen, oxygen and nitrogen at atmospheric temperature, atmospheric pressure and room temperature. It varies about 0.1 to 0.05 microns, okay. That is about 100 to 50 nanometers. That is the distance traveled by a molecule between successive collisions. Okay. 100 to 50 nanometers or 0.1 to 0.05 microns is the estimate of that distance. The molecular diameter is in angstroms. So, a molecule travels approximately 200 to 500 times its diameter before it collides. Okay. So, it travels a very long distance between successive collisions of the molecule. So, that is the order of magnitude of the mean free path. Okay. So, and finally, based upon this we had estimated what is the diffusion coefficient. I had given you a more exact expression for the diffusion coefficient based upon the molecular diameter, the temperature and the number density in a binary gas diffusion. Okay. And we had got an estimate for each of these, and we had used it to actually calculate the diffusion coefficient in of water vapor in air. And the exact expression has constants here, 3 by 8, 1 over square root of pi, etc. Okay. So, it has these constants in here, okay, 3 by 8, 1 over square root of pi, etc., which you cannot get by a simple estimate of the mean free path and the RMS velocity, but these require more complicated calculations, and if you go through these calculations you will get this expression for the diffusion coefficient. We had used it to estimate the diffusion coefficient of water vapor in air, and we were getting approximately the correct results, assuming specific hard sphere diameter, molecular diameters for the different molecules. Okay. And that result was very close to what is actually measured in experiments, despite the assumptions made that the molecules are hard spheres and it is a dilute gas using kinetic theory of gases. Okay. So, the diffusion coefficient in gases is of the order of 10 power minus 5 meter square per second. Okay. What about the diffusion coefficient in liquids? Okay. Okay. The essential difference between liquids and gases in the molecular picture is that in a gas the molecules are separated by a distance large compared to the molecular diameter, and between intermolecular collisions they travel a distance that is large compared to the molecular diameter. We saw based upon estimates that this distance is anywhere between 200 and 500 times the molecular diameter. In a liquid, in contrast, the molecules are very closely spaced. Okay. The distance between molecules is comparable to the molecular diameter. Okay. The distance between molecules is comparable to the molecular diameter. Okay. So, the molecular diameter dm for most common molecules will be in the range 1 to 10 angstroms. Okay. So, the microscopic scale in this case is the molecular diameter. Okay. So, if you were to make an estimate based upon the molecular diameter itself and the root mean square fluctuating velocity, that the diffusion coefficient is equal to some constant into dm into Vrms. Okay. Just as we had used mean free path in gases, if we just go ahead and use the molecular diameter in liquids. I had told you that the Vrms is determined from equipartition of energy. Okay. This equipartition law applies for both gases and liquids. Okay. This equipartition law applies for both gases and liquids, and therefore, Vrms is exactly the same in liquids as it is in gases. Okay. So, we had estimated Vrms is approximately equal to 500 meters per second in gases like oxygen and nitrogen, which is approximately the same as for example, the speed of sound. Okay. In gases. Okay. It is not the same as the speed of sound in liquids, because the expression for the isothermal compressibility turns out to be different. We will not go into that, but Vrms is still determined by the same equipartition 3 kBT by m. Okay. Whether it is in gases or liquids, this equipartition has to apply, and therefore, the Vrms is approximately 200 to 500 meters per second. Okay. And the diameter of a molecule is approximately 10 angstroms to 1 angstrom. Okay. 10 power minus 10 to 10 power minus 9. Okay. Meters. Okay. So, if I just assume this as the estimate, I would get the diffusion coefficient as 10 power minus 7 to 10 power minus 8 okay, meter square per second. Just multiplying 10 power minus 9 to 10 power minus 10 by 10 power 3 or 10 power 2 okay, as the Vrms magnitude. Okay. So, this is what I would get just from a simple estimate. Okay. It turns out that this estimate is actually an overestimate. Okay. This is an overestimate. Okay. The actual magnitude is approximately 10 power minus 9 meter square per second for the diffusion of small molecules, okay, for O2, N2 in water, okay, for example. And it could go very small, out to 10 power minus 13 meter square per second for large molecules such as proteins, etc., in water. Okay. So, therefore, this simple picture gives an overestimate okay, of the diffusion coefficient. Okay. And I will try to explain the reason why it gives an overestimate. Okay. The diffusion of molecules requires the physical transport of a molecule. Okay. So, if I have a densely packed okay, molecular assembly, okay, and if one particular molecule has to diffuse in one particular direction, okay, if one particular molecule has to diffuse in one particular direction, say this is a solute molecule in the solvent which has to diffuse in one particular direction. This requires the collective cooperative motion of all the other surrounding molecules, okay, because in a densely packed assembly, unless the surrounding molecules move in a cooperative manner, a molecule cannot move in any one particular direction. Okay. In fact, the picture in the case of liquids for molecules is that all the molecules are in a cage that is formed by neighboring molecules, okay, and they are basically having a random motion within that cage itself, until there are rare rearrangements where the molecules surrounding this molecule can rearrange so that this molecule can move in one particular directions. Okay. So, that requires the cooperative motion of all the surrounding molecules, okay, and that is a very rare event. Okay. The cooperative motion of surrounding molecules is a rare event, and because of that the diffusion of one particular molecule in any direction requires a cooperative motion which slows down the diffusion coefficient in comparison to the estimate that I had given over here. Okay. And therefore, the diffusion coefficient in of small molecules in water, for example, will be of the order of 10 power minus 9 meter square per second for small molecules, and 10 power minus up to 10 power minus 13 meter square per second for large molecules. Okay, so, we cannot estimate this based upon the diffusion coefficient itself, upon the mean free path and the fluctuating velocity, or the molecular diameter and the fluctuating velocity. Okay. So, how do we estimate the diffusion coefficient in liquids? Okay. The estimation of the diffusion coefficient is from a phenomenon called Brownian motion. Okay. Brownian motion refers to the motion of particles of approximately a micron or so, okay, a micron or smaller in a liquid. Okay, for example, it could be in gases as well, but I will just deal with the liquid here. Okay. The molecules of the solvent or the suspending medium, in this case the liquid, are much larger, are much smaller than this particle itself. Okay. And these molecules of the solvent have rapid interactions or collisions with the surface of this larger particle. Okay. They have interactions with the surface of this larger particle. Okay. Now, because of this, on average the force, net force is always 0, okay, because you have at equilibrium the probability of colliding from the left side is equal to that on the right side, and the molecular velocities are all isotropic. They have equal root mean square velocities in all directions, and because of that there is no preferred direction for the velocity field itself. Okay. However, instantaneously there could be a force that is exerted because of the instantaneous asymmetry in the force exerted by the molecules. Okay. And this instantaneous asymmetry in the thermal fluctuating forces causes what is called Brownian motion, where you will see this molecule undergoing some random walk around its original location. On average the velocity is equal to 0, but the mean square of the displacement is not 0. Okay. So, the displacement is with equal probability in all directions, therefore, the net displacement on average is equal to 0. Okay. That is, if I started off a large number of these colloidal particles at the center and washed all of them, they would all diffuse, but if I take the average location of all of those, that will be at 0 itself. The mean square displacement, okay, is related to what is called the Brownian diffusion coefficient, and we had solved this using dimensional analysis previously. This is equal to 6 times the Brownian diffusion coefficient times t. Okay. So, if I plot r square as a function of time, okay, I will get something that goes linearly, okay, with a slope that is equal to 6 dB in 3 dimensions. In 1 dimension it is 2 dBt, in 2 dimensions it is 4 dBt, and 6 dimensions it is equal to 6 dBt. Okay. And this mean square displacement is executed by the Brownian particles, okay, in a liquid consisting of small molecules. Okay. And this diffusion coefficient is due to the thermal fluctuating forces exerted on the particles. Okay. This diffusion is due to the thermal fluctuating forces exerted on the particles. The diffusion coefficient actually has to increase as the force increases, because as the force increases, the net asymmetry in the forces on the particles will increase. Okay. So, this diffusion coefficient is a function of the thermal energy, okay, and it can depend upon the molecular diameter, okay, because the size of the particle also matters. And there are two other parameters, which is the density of the fluid and the viscosity of the fluid. Okay. As we had discussed when we did dimensional analysis, this process usually takes place at very low Reynolds number. Okay. Therefore, the density is not a parameter. Okay. The density is not a parameter, it is only the viscosity that is a parameter. Okay. And just based upon dimensional analysis, if you recall, we had got an expression for the diffusion coefficient Kb T by some constant into mu into the molecular diameter. That constant from Stokes' law for diffusion would turn out to be 3 pi. Okay. This factor of 3 pi cannot be determined from dimensional analysis. However, you need more detailed calculations for that. But to within a multiplicative constant, the expression for the Brownian diffusion coefficient is the same, where Kb is the Boltzmann's constant and T is the absolute temperature. Okay. For the mass diffusivity in liquids, a similar expression is used for making estimates. Okay. It is not quantitatively accurate, okay, because of two reasons. One is, this expression is strictly valid only when the particle diameter is much larger than the molecular diameter. When the particle diameter is comparable to the molecular diameter, this expression is not valid. Okay. However, it can still be used to make quantitative estimates. Okay. So, first thing is that we use the same expression when the particle diameter is comparable to the molecular diameter for the molecular diffusion coefficient. Okay. There is an approximation there where it can be used to make order of magnitude estimates. The second approximation we make is to say that this Brownian diffusion coefficient of a single particle is the same as the diffusion coefficient in Fick's law for the concentration field. Okay. This once again is an approximation. Brownian diffusion was calculated for an isolated particle, okay, one particle in a fluid. The concentration diffusion is for a large number of molecules where there is a gradient in the concentration. If you want to make an analogy between concentration diffusion and Brownian diffusion, one has to assume that the molecules that are diffusing, the solute molecules, are small in number compared to the solvent molecules, so that the interaction between solute molecules does not affect the diffusion process. If you make these two assumptions, then the diffusion coefficient in a liquid can be written in an analogous fashion as Kbt by mu times the molecular diameter of the solute molecule that is diffusing. Okay. We have related the concentration diffusion to the Brownian diffusion, and we are using the same expression, substituting the molecular diameter for the particle diameter in this case. Okay. And if you make these two assumptions, you can get an estimate for the diffusion coefficient in liquids. Okay. So, let us get let us solve a specific example. Okay. Okay. Diffusion coefficient of nitrogen molecules of diameter (3.8 into 10 power minus 10 meters, 3.8 angstroms) in water at 300 Kelvin. Viscosity of water is 10 power minus 3 kg per meter per second. Okay. So, how do we estimate this diffusion coefficient? Okay. We know that the diffusion coefficient is equal to kb T by 3 by mu dm. Okay. Kb is 1.38 into 10 power minus 23 joules per Kelvin into 300 Kelvin divided by 3 pi to mu is 10 power minus 3 kg per meter per second into the diameter is 3.8 into 10 power minus 10 meters. Okay. And you can easily verify that this will have dimensions of the diffusion coefficient. Joules is kg meter square per second square, okay, kg meter square per second square, and the Kelvin cancels out. In the denominator you have kg per second. Okay, so ultimately you will get meter square per second. Okay. And this turns out to be equal to 1.6 into 10 power minus 9 meter square per second. Okay. So, this is the estimate based upon the molecular diameter. Okay. The actual quantitative result, okay, that is the experimental result, is 1.9 into 10 power minus 9 meter square per second. Okay. So, the estimate that we have made is actually quite close to the actual experimental result. Okay. It is within about 20% or so. It is the correct order of magnitude, 10 power minus 9 meter square per second. And this is the kind of diffusion coefficient you will have, okay, in small molecules in water. In this particular case, the diameter is 3.8 angstroms. Okay. For larger molecules like proteins, etc., okay, you could have a diameter which goes into hundreds of nanometers up to a micron scale. In that case, the diffusion coefficient will be even smaller, okay, because the diameter in the denominator, if it increases by a factor of 1000, the diffusion coefficient will decrease by a factor of 1000. Okay. And of course, Kb and T remain roughly the same, and the viscosity of water is in the range of 10 power minus 3 kg per meter per second. So, because of that you get a diffusion coefficient in the range 10 power minus 9 to 10 power minus 13 meter square per second for small molecules to large molecules in water. The diffusion coefficient will be even less if you have very viscous fluids. Okay. If you have very viscous fluids, the diffusion coefficient will further decrease because the viscosity is larger. Okay. So, this is the range of diffusion coefficients you get, and we managed to get the correct order of magnitude and a relatively close diffusion coefficient even numerically, okay, by just using the Stokes-Einstein relation. Okay. So, I should note that this is called the Stokes-Einstein relation. And in here we have used Stokes' law for the drag force on a particle. Okay. We have used Stokes' law for the drag force on a particle. Okay. So, you get a fairly quantitatively accurate result for the diffusion coefficient by using the Stokes-Einstein relation. This result becomes better if the solute size increases, okay, because as the size becomes larger, the Brownian diffusion coefficient becomes more accurate. Okay. It is strictly valid only when the size of the particle is much larger than that of the molecules, but we are extending this to molecular sizes in order to get quantitative estimates of the diffusion coefficient. So, this completes our discussion of diffusion in gases and liquids. In gases, it is due to physical transport of molecules across a surface. Diffusion coefficient is mean free path times the diameter. In liquids, the mass diffusion is a slow process because mass diffusion requires the transport of molecules physically across a surface. And because this requires the cooperative motion of other surrounding molecules in order to create space for a molecule to diffuse, the estimate for the diffusion coefficient is even smaller than what you would expect, simply based upon the microscopic length scale and the root mean square fluctuating velocity. The Stokes-Einstein relation can be used to provide an estimate. This completes our discussion of diffusion of mass. In the next lecture, we will discuss diffusion of heat and then go on to momentum diffusion. So, I will continue this in the next lecture. I will see you then.